10 minutes because I want to make sure that everyone has a chance to arrive so we can, cover some of the details. But as I said in the meeting chat, all of the future live learning sessions that I do will start at 6. So if you're late, there's always the recording that you can review afterwards if you need to catch up on those first few minutes. Okay, so welcome everyone to Deep Learning. My name is Alex. I work at the University of Toronto. I'm a senior research associate at a place called the Center for Analytics and AI Engineering. Um, a little bit about me. I've been doing artificial intelligence research for my whole academic career. I did my bachelor's degree as well as my master's degree in AI. And I've been working as in a staff position at U of T for the last 5 years, where I do a lot of teaching around AI. So I like to think that I have a good bit of experience in explaining this stuff, and hopefully you'll agree by the end of this course. So a little bit of logistics before we go into some material. I'm going to talk a little bit about the format of this course, and then give some background/context for deep learning as a concept. And then the very last part of this lecture, we'll sort of start the main material. This is kind of a scary slide to have as the first slide. I apologize for that. Something to know about deep learning is it's an advanced topic, right? Deep learning has never been more accessible than it is now, which is great. Using artificial intelligence models as well as training them, developing them is now something that's really, really easy to do, at least in principle. But the concepts that actually power deep learning are still fairly complex. And so my goal with this course is not just to show you how we can utilize these tools, which I think is actually quite accessible, but also to leave you with an understanding of how they work. And particularly why I think this is important is because it's a very shifting field, right? There's new technology coming out all of the time. And I want to equip you with understanding that allows you to get what's going on with stuff that doesn't even exist yet. So, in 2 years, in 5 years, when there's some new AI that, doesn't currently exist, my hope is that what we talk about in this course will sort of empower you to better understand those things, even though we're not going to cover them specifically here. I hope that makes sense. But so this is a challenging course in terms of the concepts. It's my aim to make that as accessible as possible for you. So I say that it's challenging. I don't want it to be challenging, but I find that in practice a lot of it can be. So with that in mind, I really love questions. If you have a question during the course, you can at any time raise your hand in Zoom or post it in the meeting chat. I like to sort of stop and answer questions as they come in because I think it's a little bit better for if I'm explaining something and you're not understanding it, then there's a risk that other people are in the same boat. And maybe I could just be doing a more thorough job. So I would rather stop there and add that more detail instead of have you come back at the end and everyone else is confused, but you now have an understanding. So yeah, lots of questions are great. And I will do my best to answer as many of them as I can when they're asked. Obviously, if we get like super sidetracked with questions, then I might leave some to the learning support staff who I will ask to introduce themselves in a second, just so that we do have a bit of a pace as well. So in general, the very high level concept of this course is to understand how and when we should be using deep learning as opposed to other tools. Because I'm something of like an AI skeptic in the AI research field. The technology is very powerful, but I think it's worth thinking of deep learning as one tool in a toolkit rather than the only tool. So it's important to get that understanding of when deep learning is useful and when it's more useful than other tools. We're going to talk about how it works. How is in quotation marks because there's sort of an endless level of depth that we could get to, and I'm trying to avoid having too much math. So there will be some math, but for the most part, we're going to try to stay at sort of the conceptual framing. And then frontiers of deep learning is the new stuff, the cutting edge. So I know that everyone is probably interested in understanding a bit about how large language models work. We'll try to get to that as well as some other cutting edge technologies. And then on the practical side, we're going to understand how to use deep learning. So how to build models, how to train them, and how to properly evaluate them, to see if they're working in the way that we want them to. So we'll work with NumPy, which I think you're probably familiar with already, as well as TensorFlow, which is one of the two sort of largest toolkits for deep learning at the moment. Within TensorFlow, there's an even simpler interface called Keras, and that's sort of what we'll be starting out with. And then more broadly, just working on knowledge for building and training deep learning. So what the considerations are, and how we use this technology in a way that is effective and that we know is actually working. Okay, so the next part of the class is going to be talking about a little bit of the background here. Before we do that, I want to give a second for our learning support staff to say hi to everyone. I think you may have met them both already, so maybe just a quick hi, but we've got Edward and Tianyi here tonight, and Emma will be here tomorrow night as well. If the two of you want to say hi.
Hello everyone. Yeah, it will be the same 3 learning supports as the last course, 2 weeks, well, from the last 2 weeks. So, I'm excited to keep working with you all. Anything to say, Kenny?
And Tianyi?
Hi, good evening, everyone. It's nice to see everyone again. Feel free to reach out if you have any questions. Thank you.
Thanks, guys. Yeah, so you've met them already, and they'll be here to support through this class as well. And also, I have my cat on my lap, so she's probably going to be joining some of the time as well when she feels like it. Okay, so let's get started. At a very high level, what is deep learning? So there's a lot of terms in artificial intelligence that I think get used almost interchangeably, and it can make it very confusing to outsiders as to what the difference between a lot of these terms are. So deep learning, neural networks, AI, machine learning, they have specific meanings, but they often get used pretty interchangeably. I'll do my best in the course to be specific with my language in a way that is clear. But this course is called Deep Learning. And really all that means is a neural network that has more layers or more modules within it. So it sounds like an intimidating concept, but really deep learning is just the name for the modern usage of neural networks. And we'll talk more about neural networks and how they work, don't worry. There's other ways to think about it, though. One is that deep learning is a toolkit that empowers us to build nonlinear, hierarchical, and abstract representations of data. Throughout this course, I'm going to present you with a way of sort of thinking about how a neural network actually works that is really built on this framework of changing our understanding of the data itself, so that we can make the problem that we're trying to solve easier. That's just a little hint forward at that. But we'll come back to these concepts of what it means for it to be nonlinear, what it means for it to be hierarchical. And I think abstract is already somewhat clear. It's abstract in the sense that we don't really have a clear understanding of how the internal mechanism of the network is making its decisions. We can test them and we can follow the math through, but it's very difficult for us to sort of specifically say this part of the network is doing this and this part of the network is doing that, which we'll talk about more as well. Very helpfully, deep learning is highly flexible models that allow us to manage many different kinds of inputs and outputs across many different sizes. This makes it really versatile in a way that other related approaches sometimes aren't. And then lastly, we'll at a few points talk about deep learning as differentiable functional programming. I don't know how many people are familiar with or have heard of functional programming, but the concept here is that we can think of a neural network as functions that are applied on other functions. And again, we'll talk about that more in detail. Actually, later on in this lecture, I'll talk about it in a bit more detail. And the reason that we'll think about it that way is it really helps us to understand what's going on under the hood in toolkits like TensorFlow and PyTorch, because they really rely on that framework in order to make it easy for you to build and develop models without having to do a bunch of your own coding. Okay, so that's what deep learning is. But why is deep learning such a big topic now? There's a few big reasons for this. The first is that the algorithms are better and the understanding is better. I have a great video that I'm going to show you 5 minutes of tomorrow. If after that you're interested, I highly recommend you watch the whole thing because it talks about the history of deep learning and of neural networks. The very first neural network was developed in like the 1930s by the US Navy. It was this massive machine, and it was a single layer of neurons with physical dials that had to be adjusted in order to change the weights and the biases. It didn't work very well. It basically could tell apart left and right in like a pattern of lights, and that was about it. So, you know, the field is actually older than some people may realize, but what has changed is that we've developed better algorithms to actually utilize the fundamental concepts. So we've known for almost 100 years now that it's possible, in principle, to have this like artificial neural network, but it's taken a lot longer to get to the point where we can train it in an effective way, where we can build it in a way that is computationally efficient, and that's sort of the first part here. The second part is computing power, right? So computers have been getting faster and more powerful at a substantial rate for decades. And it's only within the last 10 or 15 years that we've reached a level of computational power that it's become really realistic to train deep networks. They require a lot of resources, especially when we get into the modern like large language models and things, a lot of resources in order to train. But even the things that we'll be running on our own computers, that wouldn't have been possible even 10 years ago. That's how quickly the technology has changed. More than just the raw computing power, we've also seen in that since 2012, really, this realization that we can utilize graphics processing units, GPUs, to very, very efficiently do a lot of the computations that are involved within a neural network. The gist of it is that they realized GPUs are designed for doing graphics, like for video games, for animation, for movies, things like that. It's all vector based. And they realized in the early 2010s that it was possible to express all of the computations that go into a neural network in those same vector formats. So they could utilize the very efficient mathematical computation that these GPUs could do for neural networks. Since then, we've seen an increase in specialized computing hardware that is specifically for deep learning. So these are kind of like a version of GPUs, where GPUs were originally designed for graphics. TPUs, which stands for Tensor Processing Unit, is specifically designed for machine learning, for neural networks. They're similar, but there's some key hardware differences that are not really worth getting into. Next, data availability. So unlike other types of machine learning and statistics, deep learning is heavily, heavily dependent on the quantity of data that you have available. As we'll see, the performance or the efficacy of a deep learning model is really linked to the amount of data that you have available. And as those models get larger and more sophisticated, we need more and more examples in order to get the performance that we're looking for out of those systems. And so that means that it's only in recent decades where the amount of data that exists has become so vast that we have reached a point where we can train these models with enough different examples to work successfully. And I think it says something that a small data set in artificial intelligence in deep learning now would be 10 or 50,000 data points. There's a long time where that would have been considered a huge amount of data, and now it's trivial for us. And we can see that sort of this graph here is sort of showing that performance in machine learning is fairly similar for other types of learning algorithms as well as deep learning with small amounts of data. I might even go further and say that other learning algorithms are often much better than deep learning when we have a small amount of data. But then as the amount of data increases, the capability for deep learning to continue to improve its performance is much higher than those other types of methods. There's a greater capacity for learning complex pattern recognition, essentially, from the data. And lastly, and this is one that I think can often kind of get overlooked, is the availability of open source tooling and models to the power of deep learning. So it is not for nothing that in the world of deep learning, all of the tools that we need to use essentially are free. Anyone can use them. They don't cost any money, and they're developed by, they're developed by a mix of companies and open source communities. TensorFlow and PyTorch, which again are the two largest of these toolkits, are respectively primarily developed by Google for TensorFlow and Meta or Facebook for PyTorch. So those companies are sort of funding most of the development, but they are themselves open source. So anyone can go in and contribute. Anyone can go and look at the code and understand how it works. And yeah, there's no cost to using them. And similarly, there's a culture of making data and models available for people to work with, which is really, really good for the development of the technology, because anyone can work on top of the work of others. So it means that there's a lot more speed in terms of that collaboration in development. Yeah, so I think that's something that's really worth appreciating as well. Now, even I've been teaching artificial intelligence concepts for the last 5 years, and even in that time, the amount I've had to spend explaining to people that AI is a part of our modern world has dropped. It used to be that even in 2020, I had to sort of explain this to people a lot more, and now I think everyone is well aware of how pervasive AI is in our lives. But I still think that we largely think of that as like, ChatGPT. And it's important to reflect upon the fact that there's a lot more kinds of AI out there, integrated in a lot of different ways. So next part is I'm going to talk through some examples of the different kinds of AI or of deep learning technologies that we'll look at through this course. So the first is speech to text. Speech to text is taking in audio from a microphone, from someone talking, and converting it not only to a digital representation, which would be like a recording, but to text, written text that represents what that person is saying. This is something that has been around for 20 years at this point, but what's really remarkable is that the ability to do this has not only, it's way more effective than it ever used to be. I don't know if anyone remembers the early days of YouTube's automated captioning. It was like incomprehensible almost all of the time. Whereas now your phone can do very, very high quality transcription right on the device without even having to send it off somewhere. That very first version of Siri that they released, it would record you and then it would send that recording to a computer somewhere in Silicon Valley, and they would do the processing off-site and send the text back to you, because that was the level of computation that was required. But now it just happens directly on the device, which is more secure. It's also faster. Yeah, so speech to text is really it's 2 steps, right? The first step is taking the input from the microphone and converting it into a meaningful sound representation. And then the second part is figuring out what words are actually being said in that. And this is not just a matter of like matching the sounds to letters or the sounds to groups of letters, but it actually requires a level of understanding of what's being said. It's hard for us to appreciate a lot of the time, but there are many, many sounds that can be interpreted different ways if you have no understanding of the context on either side of them. So it's really being able to understand the full sentence as a single entity, or as like part of a larger entity, that enables successful transcription technology. I won't go into that in too much detail here, but it's worth thinking about and understanding that there's a real depth here that is being accomplished. The next is computer vision. So computer vision is like the real success story of deep learning in the 2010s. The top left there, Alex Krizhevsky, AlexNet 2012, that was like the real jumping off point for deep learning based computer vision. And what they're showing here is that they can reliably predict what the subject of these very small images are. So mite, container ship, motor scooter, leopard. That is the most basic version of this task, right? And we'll talk about in our vision lectures why that's actually not super useful in practice. But we'll work through all these examples in vision, and by the time you get to modern computer vision in the bottom right, it's not just about telling you what is at the center of an image, but it's about labeling every single part of that image and what that thing is. And this can be done now in real time. So not only are they able to label everything independent of how much stuff there is, but they're able to do it at an incredibly fast pace, which is obviously critical for things like self-driving cars. There's other technologies where being able to do that is really important as well. Vision goes further, though. It's also really useful in the medical field. Computer vision has made a lot of diagnostics in medicine faster and more effective. There are many, many studies now showing that computer vision models are more reliable than doctors in specific cases when it comes to identifying things like skin lesions that may be cancerous. I say specific because we have to be clear when we talk about this stuff where deep learning is more powerful than a person and where it's not. And there are certain well understood areas where deep learning is really effective. That doesn't mean it's great at everything. On the bottom there, we have face recognition. So we'll talk about face recognition more in the vision lectures as well. This powers things like, when you unlock your iPhone with Face ID, that stuff has to happen very quickly in a secure way. And it has to be able to distinguish your face from someone who looks very similar or from someone who I'm sorry that it's so small, but in that bottom left, what they're showing is actually different people, but in like exactly the same position and lighting, and showing that the model is able to distinguish that. Because it shouldn't be sufficient that somebody just like stood in the same clothes as you in the same lighting, but that can be challenging. So there's a lot in computer vision. I think it's a super interesting topic, and we'll talk about it later in the course. And then next is natural language processing, NLP. And so this is the scope that large language models fall under, but that's a fairly new development in the field. Natural language processing actually like well predates deep learning. It's a field of research that cuts across computer science, philosophy, psychology, early childhood development. Really, really interesting stuff. Google Translate has actually been a major driver of a lot of the technology in deep learning around natural language processing. In fact, the transformer, which is the piece of neural network architecture that powers models like ChatGPT, was originally developed for Google Translate in order to improve the quality of translation. And what that sort of figure in the top right is trying to show is that there's a lot of interest and research in understanding how to translate between pairs of languages where we don't necessarily have a lot of examples of those languages being translated between each other, but instead going via some third language. So in that example, they're showing going from English via Korean to Japanese, because there may be more examples of English to Korean and then Korean to Japanese or something like that. So we can take advantage of pairs of languages where we have a lot of data and use that to actually jump through the hoops and get to pairs of languages where we don't have a lot of data. And that's incredibly useful when it comes to translation for very low resource languages, as we call them. So languages that not a lot of people speak, or there's not a lot of data out there that's available. The bottom figure there is showing a model that tries to parse out the grammar of a sentence. It turns out that figuring out the grammar of a sentence is an extremely hard problem, and it's one that even large language models today can often struggle with. Although we've made a lot of steps even since this paper in 2015. And of course, I don't think that I really need to explain that natural language processing is something that we interface with a lot now. There's a lot of, transition from older approaches to large language models. It's still worth noting that a lot of what we see as chatbots today aren't using these sophisticated large language models, but we're moving more and more in that direction over time. And of course, we don't have to use these things in isolation. We can also combine these concepts together. So vision plus natural language processing, you can tell ChatGPT to make you an image, and that's a combination of these things where it's combining a conceptual understanding of the language with a conceptual understanding of the patterns in pictures. What we see at the top there is an early attempt at a question answering model. So it takes in both a question and a picture that question is about, and produces a textual answer at the end. I think this is something we almost take for granted now, but in 2017, which was not that long ago, this was an extremely difficult problem to solve. And then below, what we're seeing is automated image capturing, image captioning. So creating a description of an image just by using artificial intelligence. More sophisticated computer vision techniques now allow us to produce new images, as I just alluded to. This is also something that has come a very long way in the last decade. So 2015's Google Deep Dream was like one of the early examples that saw a lot of popular attention. You might remember it from that time as like people would talk about these weird, creepy images that Google was generating with lots of eyeballs everywhere. And you can sort of see that there, that it has this very strange look to it. They weren't going for that. That was just the best that they could accomplish at the time. The top right is showing what's called style transfer. So taking an existing image and then converting it into the styles of different things. And then below, what we see is an example of AI image upscaling. So taking a lower resolution image and making a prediction about how that image would look at a higher resolution. There's a question from Antonio. I think the bottom images in the last slide were an example where the image and the wording did not match.
The back flip, there's water, and then the machine thinks that there's a wakeboard, but it's not.
Yeah.
The young girls, one is an adult, like things like that.
You're absolutely right. So good for catching that. This was the state of the art in 2015, right? Was that these captions were close enough to the truth, and that was considered impressive. Today, we actually have technology that can much more reliably caption images, but you might imagine it's a very sophisticated problem. Andrej Karpathy, who wrote that paper, I believe works at OpenAI now. So that's sort of where that's gone. Yeah, so we'll talk about that in more detail. It's very interesting. And yeah, image upscaling. Now this is in TVs, right? If you buy a brand new Samsung TV, it uses deep learning. I mean, if you turn it on, it can use deep learning to automatically upscale the video that you're watching in real time to the highest resolution that the TV has. I think a number of the big brands do this. Kevin says that Andrej Karpathy left OpenAI. Okay, he was there at some point. So yeah, this was state of the art in 2016. Now it's ubiquitous consumer technology. And again, in 2017, the state of the art for generating pictures of like imagined pictures of people was this NVIDIA effort. They didn't really have a lot of control over what was coming out. They could just make it generate something that looked fairly realistic. Of course, if you look at these for too long, you start to realize that they don't look quite right. Some of them are worse than others. And that was as good as it got in 2017. And now, 8 years later, we have substantially more powerful image generation, which this was an early attempt of as well. So it starts with a text description, and then it uses that to make a prediction of what the corresponding image would look like. Closer to what we have now, OpenAI has DALL-E, which is able to generate more realistic images. This is earlier than what we have now, and even that is not super great. the speed of this technology improving has been really, really rapid. We're moving on from natural language processing. I'll also highlight deep learning in the world of science. So deep learning has made a huge impact, particularly in medical sciences, in a lot of very complex questions where we need to, do very sophisticated analysis. Here we're looking at an example of deep genomics. So genomics is the study of genes and how the expression of genes affects what happens in the body. And it turns out that we can actually represent a lot of genes and genomes in a similar way to how we handle text, because it is almost like a language, right? It's a structured description of what should happen. It's a set of instructions. And so we can use very similar technologies to understand how these genes work, what they're doing, and things like that. So it's made a huge impact in that field. A really big contribution from deep learning as well is in protein folding. So for a long time, every protein is folded in some complex way that has an impact on what it does. I'm not a geneticist, so I don't know a ton of detail. For the longest time, the way that they would figure out how these structures actually looked was by trying many combinations or permutations of that structure and testing if it behaved the way that they expected. This is extremely time consuming. It required a ton of computational power, and it took a long time to get to the correct answer. With deep learning, we're now able to much more intelligently make predictions about the structures of these proteins. And the result of that is that they can massively speed up these protein folding experiments. The newest version of AlphaFold that came out maybe earlier this year or late last year actually uses a similar technology to how image generation works in things like ChatGPT. So they've moved in that direction because it turns out it's a highly effective technology for predicting how these proteins are folded. But we can go beyond just genomics. On the left there, we have a chemistry example. So we can take a chemical formula and use this model to make predictions about what properties that molecule is going to have. That's extremely useful in things like materials research, as well as drug discovery, things like that. And on the right, we have an example of physics simulation that is being accelerated by a neural network. So it's 100 times faster than the standard version that just uses raw computing power to predict all these particles. By speeding it up with predictions from a neural network, these things can happen a lot more quickly, which means that experiments can happen at larger scale or can be finished faster. The last sort of subject area that I'll talk about is deep learning for games. So I think a lot of people have probably heard of AlphaGo when Google was able to produce this AI model that was very good at playing Go, that beat some of the best people in the world. And there's many other examples of working on this area of deep learning in game AI. So on the left there, bottom left there, you can see an example of learning to play Atari games. The reason this is noteworthy is that they would show the game screen to the computer and they would give it the available inputs, but they wouldn't tell it what it meant to be winning or how the game worked. They would just show it the screen and it would learn over time, that part in the top right is my score and I want that to go up. And that was actually part of the learning process. So totally from scratch. Bottom right is similar for StarCraft 2. Not a lot of people know this, but before OpenAI became the large language model company that it is today, they actually spent a lot of time in this sort of AI video game research. So they had a lot of work in reinforcement learning, which we'll talk about in the game playing space. And that actually, when we get to large language models, that's actually something that led them to the way that those models work now. Okay, that was a lot, but I hope that it was helpful to sort of set an understanding of all of the different ways that deep learning is now being utilized and how many different applications we can use this technology for. One of my aims in this course, though, actually is to show you that even though the applications are very different, the way that the technology works is actually really consistent under the hood. That at the end of the day, for any deep learning model, what you're doing is you're taking some complex input, you're recognizing the patterns in that input, and you're using it to make a decision. And we're doing that with vector algebra and things like that. So we can apply these systems to a lot of different areas, but actually use very similar technology in order to do that, which I think is cool. So I have a little bit about how toolkits like PyTorch and TensorFlow work on that I'm going to talk about tonight before we go to the lab. But an outline of the rest of the class of all the other things we're going to cover. Tomorrow we're going to talk about backpropagation. And like I said at the top, this is an advanced topic. Backpropagation, I would say, is the hardest part of this course conceptually. I think it actually gets easier from there. So that's a little warning, because if you find that tomorrow's lecture is really complicated, don't worry, because I think it actually gets easier to follow after that point. But it's really important that we understand, what is actually happening when we build a neural network. And so that's why we cover that up front. And then we're going to work through different fields of application. So we'll talk about computer vision. We'll talk about recommender systems. So that is like when you go on Amazon and it recommends products to you, when you use Spotify, when you use Netflix. That's actually a huge field of research and a great deal of interest from companies in recommendation systems. We'll talk about natural language processing, optimization, which comes into how we train neural networks and things like that. And then lastly, we'll talk about generative models, things like large language models, as well as image generation, and unsupervised learning, which is when we deal with a situation where we're not looking for a specific answer, but we're kind of designing a system that will recognize patterns itself without knowing what patterns it's supposed to be looking for. A little bit of a practical note, the setup of this course, each of our live learning sessions is broken into 2 parts. The first is the lecture that I'll give like this for around an hour. Sometimes it's a little longer, sometimes it's a little shorter. We'll take a 15-minute break. And then when we come back, we'll work on the lab. So although it says here, work in breakout groups and discuss, I'll always open that lab by going through the first part of the lab as a live coding session. So we'll work through it together. I'll talk through what's happening. And then in the last part of the lab, there will be a section that we'll ask you to do. And what we'll do there is we'll put everyone into breakout rooms, probably about 6 breakout rooms total. And then myself and the 2 learning support instructors will circulate through those breakout groups to discuss that last part with you. And that's also an opportunity to have some more in-depth discussions, both with the other students as well as with myself and the learning support. If you have more questions about anything, really, the lecture, the assignments, the labs, we'll be happy to talk about it. All of the labs are part of the assessment for the course. The way that works is that you just need to have completed them at all. So if everything in the lab runs, if you hit run all and it all works, then you're done with that lab. So it's just a pass or fail for each one. We're working on them together. So as long as you're here, you should be able to get most of that done during the lecture. But if you need further support, there's also the working sessions on Friday and Saturdays. And you can also ask us questions, in the Slack or before and after each of the lectures as well. I see there's a question.
Hi. The lab is something that we will be doing at the end of this class, right? To just last 1 hour of the session.
That's right.
Okay, and then that lab has to be finished by the 1 hour time frame, or we can just finish it off at home.
You can finish it up at home. The first 2 of those labs will be due this Sunday with the first assignment. But if you finish them, in class, then that's great. And that's sort of the aim is for you to be able to do that.
So assignment and lab together, we have to submit in our GitHub, right?
Yeah, correct.
So how many lab sessions we'll have to submit along with one assignment per week?
So there's 2 assignments total. The structure is a little different this year because we got shifted back one day because of Canada Day. So we're actually doing this over 3 weeks, right? We have 2 sessions this week of live learning. We have 3 sessions next week, and then we have 1 session as a sort of week 3. So the first 2 labs, as well as the first assignment, are due this Sunday. The last 4 labs for the remaining 2 weeks, as well as the second assignment, are not due until Friday, the 18th of July. So the first assignment you'll have to do a little bit faster. It's new for this year, so I've designed it with that in mind. And then the second assignment you'll have much longer to work on.
So next week we will have a longer time period to finish it off, right? Because
Exactly.
as I said, 18th July is 2 weeks, so when we can finish it off. Right. Okay. Thanks.
And then I see there's also a question from Martin.
Yes, in case any of us is able to join one session, for example, in the case where you want to join tomorrow's session, so will we be able to catch up with the lab?
Yeah,
on our own?
all of the labs are actually designed so that you should be able to, complete it just from looking at the lab. So even if you aren't able to make a specific lecture, all the information is in the lab that you need to finish it. It's just that if you are here, then we're also going to work through it together. So it's just an extra opportunity to work on it.
Yeah, of course. Okay. That's good. Thanks.
And then there's a question in the chat. So LabWorks can be committed on the assignment branch. Yeah, you can just make one submission for everything that's due on Sunday, and then one submission for everything that's due on Friday, July 18th. But as long as you submit it in some format through the GitHub, and it's clear that the code is there, we'll be able to figure it out. Great. Any other logistical questions before we move on?
Also, the lab assignments and everything can be done in Silo, right? Or do I have to coordinate with my partner?
I'm sorry, I'm not sure if I understand the question.
Yeah, I mean, do I have any partner to finish it off, or I can do it myself?
You can do it yourself. We'll be working on the labs together as a large group, and then also in breakout groups towards the end. And then the assignments are just individual.
Okay, so there was a service session going on that you might need to partner with one of your team members. So that's why I was asking about it, whether that is for this deep learning session or in the future.
I don't think it's relevant to learning, no.
It's not for this session, right? This session we can do it also. Okay.
Yes.
Thank you.
And then Jennifer asks if we need to have anything set up ahead. Yes, you do. The information for that is on the GitHub, but there will be time tonight to get that set up if you haven't already. Okay, I have a little bit of like teaching material to get us started off now, now that we've finished the background, the logistics, the motivation. So I have, what is it? 10 slides, not even, and then we will take a break, and then we'll come back and start working on the first lab. Okay, so frameworks and computation graphs. Now, as I mentioned, we are going to be working with some of these existing libraries that let us do deep learning in a very accessible way. So what's amazing about these technologies is that they take care of a lot of the complexity of building a neural network for us, and they leave us at a very high level where we can just define some basic things, and then it all works in the background. That's how we will actually do a lot of the learning, but it's important that we understand what's going on behind the scenes when we actually use these toolkits, right? So at a way too high of a level, we can think of a neural network as a computation graph like this. It takes in some input x, there's a function, and it does some operation on that input and then gives us its output, which is f of x. This is almost like, this is obvious, right? Just it is a function. Specifically, we call it a parameterized nonlinear function. So nonlinear means that, unlike linear regression, where if you draw it on a graph, it has to be a straight line, a neural network can draw any kind of line on that graph. It can be, wavy, it can go back and forth, whatever. And parameterized means that there are variables that we configure in the neural network that change how it works. I like to describe these as dials. So you can imagine them as like literal dials on a machine. And the settings that we put those dials to will change what that machine does. The process of figuring out what those dials should be set to is what the machine learning aspect of neural networks is. So that's what we'll talk about a little bit today, and then in more detail tomorrow. So let's look at this computation graph in just a little bit more detail. So now we actually have some things in between our input and our output. So we take our input and we go through a series of steps in sequence that are applied to that input until we get to our output. Each of these is a very, very simple function, which is applied in sequence. And it's the composition of these functions, it's the application of these functions one after another that gives us something that is very complex. But each individual part is actually remarkably simple. So we go from x here, that's our input. And the first thing that we're going to do is we're going to multiply all of the values in x by these values w. So for each of our inputs x, we're going to have a corresponding value in w that we multiply it by. Let's imagine we have 4 input numbers, so we see 1, 0, 2, -1. Whatever numbers are in w, we're going to multiply each of those by. So 1 times 3, 0 times -2, et cetera, et cetera. The result of that is going to go into this point z. The next thing we do is we apply a nonlinear function, which we represent here by sigmoid. And this is any function that takes in that output and just applies a function that is nonlinear to it. So the most basic example is actually, hang on, I want to draw on the screen here, but I want to make sure that everyone can see it. Can you see this? If I draw? Great. Okay. So if this is our input x, actually, sorry, this should be z. So if this is z here, this point here, and it's going from here to here, so this is our output sigma. If we were doing nothing at all, we would just have a straight line, right? We would take in whatever the value is, and we would output the same value as sigma. But what we want here is what's called a nonlinearity, right? We want something that is not representable as a straight line in this sigma operation. So this can be anything. The historic example is a line that looks like this, which is called a sigmoid, and that's why we use a sigma to represent it. And this is basically a smooth version of like a 0 or 1 value. So the idea here is like, we'll come back to the understanding of this as neurons tomorrow. Right now, we're just thinking about it as functions. But the understanding is if the value is low, then we output something low. If the value is high, then we output something high. And here we only have 0 or 1 coming out. But here we sort of gradually increase the value until it's at its maximum. So here and here, we have this kind of sigma value. And then here and here, we have a multiplication of whatever we've got so far by some set of weights. All right, I know this is a lot. We're kind of just like setting this up, and we're going to talk about it more slowly tomorrow. I just want to establish this framework of thinking about computation graphs as something that we'll be using in more detail through the lectures. So you'll notice that this process is kind of repeated here, right? We have this, oh, sorry. That's just summarizing what I'm drawing. we have this pair of functions, one that multiplies by some set of weights and then applies a sigma. And then we have the same thing again, but with a different set of weights. So this is a two-step neural network, a two-layer neural network. And within each of those layers, we have the linear step of doing this multiplication by weights, and then the nonlinear step of doing some kind of nonlinear transformation. All right. Again, I know that that's a lot to throw at you. We're going to break it down in even more detail tomorrow. But the thing I want you to take away is that really what we're looking at here is very, very simple operations. We're doing a multiplication here, and then we're doing, this simple transformation here. And that's it. We just alternate those, and that builds a neural network. The power in making predictions comes from the fact that when we do this in sequence enough times, we're actually able to capture some really sophisticated patterns in the data. And we'll look at and try to understand why as we go through the course. Okay, I do see there's a question.
Hi. So the question is, as you said, X, G, and Fx, Z and sigmas are inside the graph because you drew it. I'm trying to understand where is Fx and Fx is. Like for LCR class, we had y equal to mx plus c. So is there something equation we can form it out from this?
Yeah, so maybe what I'll do is I'll step through this in like I'll give a single value example, and hopefully that will sort of illuminate what's going on here. So let's imagine that our x is literally just the number 1. Here, I'm going to pick a different color. Let's imagine that our x is literally just the number 1. Inside w, we have some number that matches with our input that we're going to multiply the input by. So let's say that our first weight is 5 and our second weight is 6. And remember, these are the dials that we're going to be adjusting when we're doing learning. So the values for these weights are what we have to discover as part of the learning process in order to get whatever we want out of this network. So we'll explore tomorrow how we use the training algorithm to figure out what the values for these weights should be. For now, just assume that they're just values that we're using. We can assume that maybe they're the best values already. So this first step is that we're going to multiply 1 by 5. And so now we're going to have 5. And then the second step is our nonlinearity. So the sigmoid nonlinearity is a very popular one. It is the earliest one that was proposed in neural networks. Another one that is somewhat surprising, but actually extremely common, is called ReLU. And so we have to extend to the negative here. So negative, positive, positive, negative. What ReLU does is any value that is below 0 is just set to 0. And then any value that's above 0 is just returned exactly as it is. So it's surprising that this works, but we find that it does. And SOD is, yes, that is essentially the formula. If we don't show it today, we definitely show it tomorrow. Yeah, we'll show it tomorrow, the mathematical framing. Sorry, go ahead.
So a linear graph that you said, the linear graph where we should be using the TensorFlow, and non-linear graph where we should be using the PyTorch. Is that what our understanding, right?
So the motivation of why I'm telling you this so early is to understand that because our TensorFlow or our PyTorch, they've already built all of these bits, right? And because they're modular, because they, you basically connect them together like Legos, we can connect them together in whatever way we want, and the system can figure out what all the math is. Can I quickly repeat yellow? So the ReLU transformation this is the graph version, but I can also write it as an equation because it's a very simple equation. So the output f of x here is 0 if x is less than 0 and x otherwise. That's it. So all it does is if you go below 0, it just says no and sets it to 0. And again, it's sort of surprising that this is sufficient. It seems like it wouldn't be useful, and yet in fact it really is. Okay, so right now we've got our 1, we've multiplied it by 5, so we've got 5. We're going to apply ReLU, and so we have a positive value, so that is going to stay as 5. Let's say that this is actually -6, so we can see what happens with ReLU here. So now we take our 5 and we're going to multiply it by -6, and in here we're going to have -30. And so now when we go to ReLU, because this is below 0, it's going to tell us actually that's just 0. And now the output of our model is 0. And this is a neural network. This is a single input value, single output value neural network with 2 layers that are doing operations. The power in neural networks that we'll see comes from the fact that we can actually do many, many different operations in each of these layers by adding more neurons than just one. So this is like 1 neuron and then 1 second neuron, and then we have the output. Okay, again, this is touching on these concepts because I want to set it up for the lab, but we are going to go into this in more detail, and we're also going to talk about it in a few different ways. So I find that this is often overwhelming at the start, but then is easier as we get into the material in the next few days. Okay. This is just a note to say that although here we are doing these functions in sequence, there's no reason that we can't do some complicated, simultaneous multiple different computations that go in different ways. We can build a graph that's as complicated as we want here. And in fact, when we go to like large language models, they do consider, different branching computations in order to, do more complex predictions. We're not going to get into detail on this. It's just a note to say that we're not limited to doing these things in like a strict chronological sequence. We can also do things in parallel. Oh, what is the star here? The star is just a recombination. So we're doing, I think, the dot product of this value with this value, and then bringing them both down here. So it's just saying that those are being recombined because we still have a single output. Yeah. Okay, so the point of me bringing all of this up is that because each of these things is a very, very simple function, it's possible for the developers of PyTorch, the developers of TensorFlow, to work out all of the math that is required for each of these simple blocks on its own, so that whenever we combine them in different ways, the very complex math that comes out of that is automatically calculated for us. That's what I am saying when I say automatic computation of gradients here. So tomorrow when we talk about backpropagation and how these networks learn, we'll talk about how we need to compute a lot of gradients within the mathematical framing of this function. And this understanding of the network as these building blocks of simple functions means that in practice, the toolkit does all of that math for us. Before these toolkits existed, if you wanted to build a neural network, first you would design its architecture, and then you would sit down and you would do a ton of calculus because you had to figure out what all of the gradients were for all of these different parts with respect to each other, and it would take forever. So it's really, really nice that we don't have to do that anymore. It lets us save on doing a bunch of calculus. And then the other part is that they have, built very, very efficient versions of these algorithms so that they can run extremely quickly. Whether that's on your CPU, whether that's on an accelerator like a GPU or a tensor processing unit, the math is very efficient here. So I'm sure that for a lot of you, you're feeling like this is some very complex and overwhelming stuff. It definitely is. But what I want to bring to you here is that as complex as this is, we can define it in Keras in 5 lines that are extremely simple. So the first line here is saying that we have a model that we're building, and then we add a first dense unit here with an input size of n, so that's how many like x0, x1, x n. and then an output size of h. So that's how many units it's going to go to in the next step. The activation is one of the words that we use for this nonlinearity here. Tanh is another function, but this could be sigmoid, it could be ReLU. And then we do the same thing again. Another dense layer here, and another activation that brings us to the output. And in these 5 lines of code, this is all that's required for us to build the model such that it's then ready to train. We don't have to do any math. We don't have to sit down and do any calculus. All of that is handled for us automatically by the system. And not only is it handled automatically, but it's efficient so that we can train it in a realistic amount of time. Okay, I see there's a question from Sneha.
Yeah, hi. So correct me if I'm wrong. So what I understood from this explanation is like we have a set of data, and what we are trying to do is find a function that fits into the data through a set of like linear and non-linear transformation, so that using that function, we can figure out the data we don't have to predict the function for that data.
I think you're most of the way there. So we are modifying the behavior of this function and moving around like the lines that we imagine, like a linear regression, for example, according to what values we put in these parameters, so that we essentially come up with a rule or like a set of patterns that dictate what we think is going to happen when we get new data. So you're in the right direction. We will look in the specifics of what that means tomorrow when we go through backpropagation. Tonight, I'm really just like presenting the fact that this is an idea. Yeah, there's another question.
Okay, thank you.
Yeah, I think this is something kind of related.
Okay.
How is it different from the ensemble function, ensemble models that we did in machine learning?
Great question. So there is a connection here to ensemble models, because one of the ways that we can think about a neural network is as an ensemble where every neuron is its own model. Now, each neuron is an incredibly simple function, right? We'll talk about the neuron framing tomorrow, but one of the ways to imagine that a neural network works is that there's individual neurons that take in input, and they, depending on if they see the values that they expect, they either output a high value or a low value. And each neuron learns a sort of specialized function that is a specific pattern that individual neuron cares about. Its output then goes to the next layer of neurons, and those neurons are looking for a pattern in the previous layer. So they say, you know, I'm neuron 2A, and when I see that neuron 1A and 1C are both excited, then I'm excited. And we can build, you know, more and more depth there. And each time we add a layer, you know, we're getting a more complex, you know, combination of these patterns. So in that way, we can think of it as being similar to an ensemble model, where it is a composition of very, very simple predictors that, when they're all together, make a more complex prediction. The difference between this and ensemble models is that this is hierarchical. So rather than just having a pool of 1,000 individual neurons that all look at the input and make a prediction, we actually compute the first set, and we use that as the input for the next set. And then we use the output of that as the input for the next set, and so on and so forth. And so each set is only making a prediction on what it's received, and then its output is being used for something different. Okay.
So essentially, we are saying that instead of maybe using an average or nearest neighbor, we are essentially sort of propagating that further. Okay.
Exactly. And this is why where did I do it? This is why I talk about this being hierarchical, right? It's this idea that, you know, each set of neurons is sort of making a prediction that is used for the next set of neurons to make its own prediction, so on and so forth. Okay, there's a question from Kevin.
Yeah, I think somebody's asking about the ensemble model, right? The key difference between the ensemble and the deep learning is one, in machine learning, regardless of the ensemble or not, we should do feature engineering. What is the data we get it? We cannot give input to the ML model. We generally do standardization, yada yada, right? Whereas deep learning, that's what I was saying earlier in the beginning, right? Deep learning is, in my view, it's auto shift. I mean, auto driving. I don't need to do the heavy lifting of the feature engineering. Whereas ML, we should do the feature engineering. And second, I think ML is not like a black box, whereas deep learning is like a black box. We really don't know what's under the hood. You're given, it's like a magician, right? Magic box. We just get the output, but really you don't know. But whereas ML, you would know, what contributed either positive or negative. That's my 2 cents on that.
Yeah, that's a great point, and it's absolutely true that one of the challenges with neural networks is that it very, very quickly becomes impossible to keep track of what is actually happening inside of the network. As Vinod says, there is research that tries to improve this or try to explain what is going on within a neural network, but the sort of the base version of a neural network is something that is very hard to explain the internal reasoning of. It requires additional effort for us to open that up and understand what's going on. Whereas there are other types of machine learning algorithm where the result of that algorithm is something that we can understand or explain. Like a decision tree, for example, the end result is something that we can follow the logic and we can see exactly why it's made the decision that it has. We don't get that luxury with most neural networks, but there are some where we do. Okay, so that is the lecture component for today. We're going to take a 15-minute break. We're going to come back at 7:30, and then we're going to get started on the lab. If you don't have the environment set up, I would recommend that you go to the Deep Learning GitHub page and check out the details on that. But we'll take our break first. Okay, so back at 7:30. Good work. Well, if you have any issues with that, please let us know either in the breakout rooms later or on the Slack. We'll be working on this one together. There's actually not a lot you have to write in this lab. It's mostly running things to see how they work. It's just at the very end where we're asking you to write some things. So there's time to get the environment set up if you need to work on that. How is the size of my screen here? Is this an okay text size? Is it readable for people?
Yeah, it's okay.
Great, perfect. Okay, so in this first lab, we are going to go ahead and build a simple neural network with Keras. As I mentioned, Keras is a high-level interface to TensorFlow that allows us to build and train neural networks while writing a very small amount of code. So it's super useful for learning about how these things work. What was I going to say in addition to that? I know that we haven't gone into a ton of detail about how neural networks work yet. That's okay. This is the side where we're going to start working with the toolkits, and hopefully you're going to see that it's very familiar in terms of how the syntax works and things like that. So tomorrow and later in the course, we'll dive into the detail of what's going on behind the scenes, but we're going to get started with the application right now. So we're going to work with the MNIST dataset. Are you familiar with MNIST? Have you seen this before? Okay, great. So I won't spend a lot of time explaining MNIST. It's a dataset of handwritten digits. We are going to load it in this first cell from scikit-learn using this load digits function. And the version of MNIST that is in this scikit-learn datasets are 8x8 pictures of these digits. So the original dataset is actually 28x28 pixels. These ones are smaller. We can confirm that in addition to the images in an 8x8 format, we also have the images in a 1x64 vector. So as if it's been unraveled from top to bottom. That's the version that we'll be working with today. In addition to the input data, we also have the actual digit that each input corresponds to. We have a matching number of input and output examples. But for the outputs, the shape is 1797, comma, which means that we have a single value in each of those, which is what we would expect. This bit of code here will take 9 random values from the data set. It will print them and show what the corresponding label is. So this is our data in image format. We can see that it sort of looks how we would expect it to. And if you run this code, it picks a random set every time, so you can run it multiple times to see different examples. But hopefully you get the idea. So these are very low resolution. They're 8 by 8, so they're even smaller than the standard MNIST. So there's not a lot of data to work on in order to make the predictions, and that will probably create an upper bound on how well our model can actually do at predicting these. But we do expect it to do okay. The next thing that we're going to do is we're going to compare different examples of the same digit. So these have all been labeled as 9s. Again, this is randomly selecting those examples, so you might get different ones. And what this tells us, early on, is that some of these are going to be hard, and it's unlikely that the model will predict them correctly. For example, this one here in the top right, I don't think that I would correctly identify that as a 9. The reason that we do this is that it's helpful to get a sense of your data and get a sense of how likely you think it is that the model will be able to achieve good performance on the task. It will inform our development because it will give us a better understanding of whether something is going well or going poorly. So in this case, there is an upper limit to how many of these I think it can get correct, even if the model is very well trained. Okay, so we've got a sense of what is in our data set. And the next thing that we're going to do is we're going to split into a training and a testing set. So in general, we try to split our data into a training and a testing set. The testing set is held out data that we don't use during the learning step. And that means that the model hasn't been shown what the correct answer is for those samples. And so that gives us an estimate of how well we expect the model to perform when it's shown actual new data, which obviously we don't have. Frequently during development, we also will add in a validation split. So we'll split the data 3 ways. And the reason that we do that is if we're testing different configurations of our model. But for now, we're just going to split into a training and testing set because we're only building one model here. We're going to verify that the data has been split correctly. What I mean by that is that we expect the sizes for the training and testing sets to match. So we have 1437 training samples and we have 360 testing samples. You can change this by changing the test size here. But this is what we would expect, and it's confirmation that this seems to have worked as we want it to. The last thing that we have to do before we actually start building our network is convert our output values from a real number into a one-hot coding representation. So essentially what this means is, we have 10 possible values that we're trying to predict between. The digit that is drawn can be anything from a 0 to a 9. Using digits is tricky because let me start over. We have these 10 possible values, and if we just ask the model to predict the actual numerical value, say, if it's an 8, then you output 8, there's an issue in the training, which is that when we compute the error, when we compute how accurate or inaccurate our prediction is, if we're predicting the real number, then the error between a 7 and an 8 would have a value of 1, whereas the error between, if it's actually an 8, but we predicted a 1, we would have an error of 7. That makes sense so far? The difference between the correct value and the predicted value would be dependent on what those two numbers are. Now, that doesn't actually make sense, right? Because an 8 and a 1 are not more different to each other as digits than an 8 and a 7 are. It's still wrong either way. And so we don't want the model to think that it sort of is better to guess that it's a 7 than to guess that it's a 1. We want it to guess the correct value, which would be 8. Essentially, the issue here is that what we're trying to predict is a category, which is the drawing of the digit and not the value. We have to sort of separate these out. So we're going to convert our targets, our outputs, from a real value to a set of categories that we're trying to predict. And so what we do is we represent each output as a set of 10 values that correspond to the digits 0 to 9. And in each place is a 0 if that's not the digit, and a 1 if it is the digit. So for example, here, the label 9 would be represented by a 1 in the very last of these columns, because it goes 0, 1, 2, 3, 4, all the way up to 9. And because it's a 9, we have that set to 1. So again, the reason that we're doing this is because each category is independent of the other categories. The difference between each of the digits, insofar as we're trying to predict the actual handwritten values, is the same. It's just as incorrect to say that this drawing of a 9, I think it's a 1. It's just as incorrect to say that as to say that it's a 7. They're the same amount of error. And so our categorical representation is better equipped to deal with that. Now, handily, TensorFlow, the Keras submodule can just do this for us basically automatically. We use this two-categorical function. We provide it with our training and the number of classes that there are in total. And here we can see how it transforms the data for us. So before we had a value of 6, and now what we have is a value of 6, a value of 1 in the column that corresponds to 6. So again, 0, 1, 2, 3, 4, 5, 6. So it's the same data, but now we've removed any kind of implication that some digits are more similar to others. They're all exactly as different or similar as each other. Does that make sense? Oh, Brian says, if you, that's actually fine. That is not an error, but a warning, I think. And it's basically just saying you could take advantage of some additional CPU things, but it doesn't currently do it. But that's fine, because we're only going to be running very small neural networks. Okay, so now that our data is in one-hot encoding representation, somebody said that they ran this code a couple of times and the output differs. So if you run this a second time, it will apply one-hot encoding to the one-hot encoding, which we don't want. And if I run it a third time, it will do it again and it'll get worse and worse. So if you find that it starts to get bigger and bigger, you should just rerun from where we load the data, which is up here. So just run all the way start to bottom. One more, or two more. Okay, this is what you should see. Is that the before one-hot encoding is a real value, and after the one-hot encoding is a vector like this. Okay. Now we have our data loaded, and we're ready to build our neural network. I see that Elliot asked, is anyone getting no module named matplotlib.colorbar? I think they may have changed the syntax for some of those things in different versions of matplotlib. Is that happening up here where we say cmap equals plot.cm.grayr? If so, I think you can just delete that and it will still work, but it will just give you weird colors.
It's happening in the first box, like at the import step.
Oh,
like import matplot.py. Yeah, that one.
Here. Oh,
Yes.
that's strange. I would try reinstalling matplotlib or trying to upgrade matplotlib then, because it shouldn't give you any kind of error this early in the process.
Okay. Let's try that.
If you're still having issues with that, let us know in the breakout groups and we can work out it in more detail.
Thank you.
Okay. Yeah. So all that's doing is saying that we want this grayscale. So it's not strictly necessary. Okay. So we have our data. We have our data pre-prepared, and now we're ready to build our neural network. So we're going to use the Keras API that makes it very, very easy for us to build a simple feed-forward neural network. Feed-forward just means that we do one forward pass through everything, rather than having those branching. If you think about the computation graph, anything like that. So when we build a neural network, when we build and train it, there's sort of 3 steps that we have to think about. The first is we define the model architecture. So we say how many layers there are, how many neurons there are in each layer, what activation functions we use, these things. The second is we compile the model. So now we say, you know, this is a complete neural network. Please do all the math in the background that's required. And this is where we define the loss function, so how we calculate the error. It's where we define the optimizer. So we'll talk about that more tomorrow. But the method of optimization that we use to train the network, as well as any metrics that we want to use to evaluate the model. So things like accuracy. And then lastly, we call model.fit. So we train the model. We give it the training data, and it runs the optimization algorithm and sets all the parameters. So first step is to define the model architecture. So that is this code here. So again, Keras makes this very simple for us. We start by saying we have this model object, and we're going to define the layers sequentially. There's another way to do it, but we don't need to worry about that. The sequential format is very convenient to use. And then one at a time, we're going to add our layers to the network until we're done. So here we're going to start with a layer of 64 neurons. This is called dense. It's the standard neural network layer. We'll get into different types of neural network layers later in the course. So 64 neurons. The activation is our nonlinear component. So if we remember from the lecture that there's 2 steps. There's the multiplication by the weights, and then there's the nonlinear function. This is telling us what we want that nonlinear function to be. So this could be sigmoid. Here it's going to be ReLU. There are many other options available as well. And then actually the Keras syntax has changed, so we don't even need to tell it anymore what the size of the input is. It will just figure that out automatically for us. So all we need to say is dense layer, 64 neurons, and we're going to use the ReLU activation function. And then we can decide any amount of neurons here, right? So we can make it more, we can make it fewer. It will impact the behavior of the model, but it is a decision that we have to make as we design this. It's not set by the data that we're using. There's a question: is there any specific reason why the input and hidden layers are ReLUs and only the output layer is softmax? Yes, there is. So we remember that the ReLU function is 0 if the value is negative, and otherwise it just does nothing, right? And so that means that the values in our neurons are allowed to be as large as they want. They can be infinitely large. That is what we want in the intermediate parts of the network, because it means that we can work with a great deal of different possible values, right? There's a lot of what we call expressivity. We can capture more complexity by being able to set these numbers to whatever we want. That's one of the reasons that we use ReLU, in fact. So for these two, we're going to use ReLU because we're not concerned with what the values of the outputs are, as long as they're meaningful to the model. This changes when we come to the output layer. So the output layer, unlike these layers, we actually have to deal a bit more strictly with what the shape and activation is going to be here. So we've got 10 neurons, and that's because we want 1 neuron for each of these possible output values, right? So what the model is ultimately going to be giving us at the end is a vector that looks like this. Now, the other thing that you'll note is that the maximum possible value we want is 1. We don't want one of these values to be like 47 because it's not meaningful for us here. These are like an indicator that says that this is the column that I think corresponds to the correct digit. So I think that this, I think this drawing is a 6, so I'm putting a 1 in the 6 column. If I put 12 in the 6 column, it doesn't tell me anything. So as a result of that, we want to use a different activation function that is going to constrain the possible outputs that the model can give us. What softmax does is it constrains the total output across all of these columns to sum up to 1. So whatever values go in here, it adds them all up and then divides each column by that total. It's like a percentage conversion, right? So it normalizes all of these values. If I had, instead of a 1 here, if I had a 47, it would add all of these up, it would get 47, and it would divide 47 by 47 and convert it to 1, which is what I would like. So the reason that we use softmax here is not to do with the sort of internal logic of the network, but instead to constrain the output to be in the format that we're looking for, which is all of the values must be between 0 and 1. We could also put sigmoid here, because sigmoid also constrains the values to be between 0 and 1, but it doesn't have the restriction that the total has to add up to 1. And that's a nice property because it means that these outputs are almost like a percentage chance that that's the correct digit. So across all of them, the percentage chance adds up to 100%, whereas if we did sigmoid, it would be independent. Okay, few questions that I want to make sure I get to. So ReLU takes more space in memory. I guess it does, insofar as using ReLU could mean that you would have to store larger numerical values. In practice, I don't think that there is a meaningful impact in terms of storing those digits. So those values. So it's less about a question of memory and more a question of how it affects the output of the model, like the behavior that is happening there. There are other conceptual explanations for why ReLU is useful. I don't want to spend too much time on it, but again, if you think about the individual neurons as essentially getting excited if they see the pattern that they care about and staying quiet otherwise, then it sort of makes sense that either they're off because they're not excited, or if they are excited, they could be a little bit or a lot. So in the lower end, it doesn't matter. There's no such thing as like being negatively excited in this context. But there is like, yes, this is exactly what I want to see, or, oh, this is a little bit of what I want to see. And that's sort of the constraint that ReLU provides there. Okay, lots of questions. Yeah, there's no disappointed neurons. Another question. Yeah, so experimentally, we find that ReLU works very well. And there are actually modern extensions on ReLU or slightly different formulations that can potentially work better than ReLU, but we're not going to worry about that right now. Okay, Ajar, you've got your hand up. What's your question?
Yeah. One of the properties that we reviewed in sort of building these models earlier was the fact that they have all these features have to be independent. Now that we are sort of generously, creating features, how do we how do we know that the features that are getting created in these hidden layers are so independent?
They are independent of the other features in the same layer, but they are strictly dependent on the features in the previous layers, right? Because the way that we define the behavior of the earlier neurons directly impacts the behavior of the later neurons. So it's a little bit different from, I think, what you would have seen before in that way. But mechanically, when we just think about the neurons in a single layer, the input that they receive is the output of the neurons in the previous layer. They have no idea how many other neurons are in their layer with them, because they don't see those neurons' inputs or outputs. They only see what happened in the previous step. And so we're guaranteed that within a layer, all of the neurons are independent because they have no way of passing information between each other. Their information is received from the previous layer and then passed on to the layer that comes after them. But the only layer that they have no impact on is actually their own layer, where they are strictly independent.
I mean, it's something like there are two scientists who came to the same conclusion at the same time.
Yeah.
But they're coming from an independent perspective.
Yeah, that's a good way of thinking about it. Each neuron independently learns what it cares about, from the previous layer. And in practice, what we find is that neurons do adopt specialized roles. And as we'll get to later, sometimes we actually want them to have a certain amount of overlap. We find that it is more robust when there is a certain amount of overlap in the patterns that they look for. But we'll come back to that. As to why we use 64 neurons here, it's an arbitrary decision. So the input size, here, let me turn off the Copilot because it's getting in the way of what I'm trying to do. The input size is 8 by 8, which is equal to 64. So the input to this network is going to be 64 values for each of the digits that we see. But then the number of neurons that we have in these intermediate layers is something that we can decide, and we can set this to whatever value we want. So this could be 1, this could be 2,500, 25,000. It can be any number that we choose. Now, how do we decide that number if it can be anything? The way to think about this is that each of these neurons is looking for a different pattern in the input data. So the more complex the data, the more patterns that we might want to see, the more neurons that we're going to need in order to capture all of those different patterns. If the data is very simple and there's only a small number of possible patterns that we're looking for, then we don't need as many neurons in order to be able to capture them all. So it's a little bit of something that we have to test experimentally. We have to try different values and see what works and what doesn't. But in general, if it's very complex data, we're going to need more neurons. And if it's very simple data, then we need fewer neurons. So 128 is probably more than we need, given that there's 64 input values and the data is very simple. It's grayscale. There's only 10 possible values that we're looking for. But we may find experimentally that actually higher numbers work better. I just want to check the questions in the chat, but I do see that someone has their hand raised. Vinod is correct that there is a sense to which ReLU causes us to lose information. And it's one of the reasons that there are other versions of ReLU that behave slightly differently, that are slightly more complex. But it doesn't matter too much. There's lots of ways for the neuron to still represent information. I can't speak to genes. That's outside of my expertise. Input layer. So Antonio asks, input layer, do you have any restriction? If we set 1 neuron in the first layer, will we just input an array with 64 values inside? So this is actually the number of neurons that are coming out of this layer that we're defining here. The input is automatically detected. So if I run this, you'll see it's very unhelpfully says that it doesn't know how big anything is. And that's because I haven't told it what the size of the input is. If I say input shape equals 6, I think that's the syntax. Input size, maybe. I had it and then I deleted it, and now I've forgotten it. Let me just Command Z. Basically, if I tell it how many neurons it should, or what the input size is, then it can tell us all this stuff going down, which
input
is
shape.
Oh, thank you very much. Thank you, everyone. And it will actually yell at you for doing this. Oh, it's because I put it in the wrong place. Great. Okay, so you see it says, do not pass an input shape. They changed the syntax here. But when we pass the input shape, we can then see the full architecture of the network. So this layer is going to take in 64 and output 128. This layer will take in 128 and output 64. And then the last one will take in 64 and it will output 10. Okay. Aya, you've got your hand up. What's your question?
Hi, yes, thank you. I'm just like still unclear on the neurons in each layer. So for example, the first layer, if you have 128 neurons, are they is each neuron responsible for like one bit of the input?
No, so each neuron gets the whole input. And so the idea here is that they each learn to pay attention to different patterns in the input data.
But they're
So-
all using the same activations and weights for
Yeah.
each layer at least.
They are, but the values of those weights when we start are set randomly. And the impact of that is that they end up moving in different directions. And that's actually one of the reasons that it's critical that when we train a neural network, we start with different values for each of the weights, because if we set them all to the same thing, they will all learn the same thing. So we need them to be set randomly when we start so that they do end up learning different things from one another.
Sorry, I had this question mentioned in the chat. Can you just explain again like the dip? Because I'm thinking of the input layers as the steps in the computation graph, which is,
Yeah.
I guess it's wrong. Each, like, what's the like difference between like how, because if each neuron is going through the computational graph flow, then what are, can you just explain the layers? I'm a bit confused.
Yeah, for sure. Let me pull that back up again so that I can show you. Actually, I think I have the PDF in here. Slides. Yep, here it is. Sorry, I just want to pull up the picture of the computation graph so we can visualize how it relates to what we're doing right now. Okay, so in the first half, I showed you a neural network like this, right? Where we have this computation graph that it takes some input, it applies the linear and then nonlinear component of a layer, it applies the linear and then nonlinear component of a second layer, and then returns the output. So this is a two-layer neural network because we're applying, there's two steps, and we're applying them once and then twice. So if we want to build this same type of network in here, then we can take out this layer. And just for absolute clarity, what we'll do is we'll say layer 1 and layer 2. They don't have to be called input and output layers. So layer 1 is going to take in X. It's going to have 128 neurons that each have their own weight associated with them. And each of those individual neurons gets the whole input. It applies its weights to that input, and it either fires a large amount if it's excited or a small amount if it's not excited, right? We then take that like excitement amount and we apply the activation function. So here that's going to be ReLU. And all that does is it says if a neuron fires out a negative value, we're going to cap that. We're going to say it's 0. So the output of this pair of functions here will essentially be our first layer, where we've now both done our first set of weights and our first activation function. That result gets fed into layer 2, where we have a second set of weights and a second activation function. These can be the same, they can be different. In our model here that we're working on, they're actually different activations. But this time we only have 10 neurons, and that's because this is what we're going to use as the output. So all 128 values from this layer are going to be fed into each of those 10 neurons. And we're saying, you know, based on these 128 values, are you excited or are you not excited? So the way to think about this is that we're learning 128 different patterns in our input data. And then in the second layer, we're saying, based on those 128 patterns, do you, the individual neuron that corresponds to 6, think that that means that we have a 6? And if it does, it says, you know, I really care about what neuron 47 has to say, and I really care about what neuron 63 has to say. But if neuron 80 fires, then it's definitely not a 6. You know, that's the sort of analogy of what's happening here. And based on the combination of those patterns, and again, the thing that is not explainable here is that we don't really know what those patterns are. We just know that they are patterns. But based on the combination of those patterns, each of those individual 10 neurons has to decide whether its corresponding value is what is being expressed or not. Is that helpful?
Yes, quite a bit. Thank you so much.
Yeah, no problem. Again, this is why I really like questions, because I want to make sure that this stuff makes sense. It's complicated conceptually. Antonio, I see that you have your hand up.
Just in the explanation you gave to Aya, so the input is, in this case, is a flat array of 64 numbers.
That's right.
And then you can send the input to 3 neurons, to 1 neuron, to 7, because all the 64 they're inside your one input.
Exactly. Each individual neuron gets the whole set of 64 values, no matter how many neurons we have.
Okay, and connecting with the question from Pulkit,
yeah,
the weights will be in every neuron. There's one array of 64 constants that we're multiplying to our input.
Not quite. There's one weight for each value it gets in. So, no, sorry, you are right. 64 is the number of inputs, and so it has one value corresponding to each of them. And so the way to think about that is each weight is sort of saying, do I care a lot about that value, or do I care a little bit? And then do I want it to be high, or do I want it to be low? If I want it to be low, I'm going to have a negative value in the weight. If I want it to be high, I'm going to have a positive value. And then the magnitude, either in the positive or negative direction, is dependent on how important that piece of input is to me. So like if I'm drawing a 2, then all of the last, the very bottom line, those values should be high. And so all of those weights are going to be high for me because I want to see that something's been drawn there. Whereas if I have a 4, most of that last thing is going to be close to 0 because I don't really care. Or in fact, maybe they'll be negative because I don't want to see any drawing at the very bottom. That's sort of the idea here.
Okay, thank you.
Okay, really good questions. And I do want to make sure there's time for the breakouts, so I'm going to push ahead, but we'll be around in the breakouts to talk about this stuff further. Okay, so I deleted a layer here because I wanted it to be close to what we had in the lecture. You don't need to delete a layer. Don't worry about it. You can just run this as it is, and we'll move ahead. So now we've defined our model, right? We've told the system what the architecture is, how many neurons we have, how many layers we have, what our activation functions are. The next thing that we do is we compile the model. There's 3 things that we're setting in here. The first is the loss function. So this is how we calculate how correct or incorrect a prediction is that our model makes. The second is the optimizer. So this is the algorithm that we actually use to set the values in the neural network. We'll come back to how that works tomorrow. And then the last are any metrics that are easier for us to understand. So accuracy is easy to understand. If I get a high accuracy, I know it's good. And so we're going to compute accuracy as well. Just briefly, categorical cross entropy basically looks at did we predict the correct column and how confident were we? So if this actually was a 6, then what we would like to see is a 1 in the column that corresponds to 6. And we don't care about the values in the other columns. We only care about that column. And that's sort of how categorical cross entropy works. Okay, so we compile. We should just get a check. We don't get any outputs. And now we're ready to train the model. And so if you've done, if you've done machine learning with scikit-learn, hopefully this syntax looks sort of familiar to you. It's the same syntax in Keras. We just do model.fit. We're going to pass our input and our output training values. We also have to specify a few other things. So the number of epochs is how many times we run the whole data set through the model. So we're going to do it 5 times. We're going to show it every sample. The batch size, again, we're going to come back to this in a little bit more detail tomorrow. It's essentially how many samples we compute the predictions for at once. So we do 32 samples at a time. It's just a computational efficiency thing. And then we're going to just use a convenience function here that will automatically take out 20% of our training data as a validation split. So we can very conveniently do validation. So if you run this, it should work successfully. It should be very, very fast because this is a tiny, tiny model. And what we see is that the loss should go down. The error in the model should go down, and our error should go up. Or sorry, our accuracy should go up. And what we really care about is the validation accuracy and the validation loss here. So hopefully, just like me, you're going to get a validation accuracy, in the 90s. That's great. It's actually better than we maybe would have expected. If you are getting any errors at this point, I see that a few people are. We can work out with you to make sure that all the packages are installed correctly and things like that. But hopefully for most of you, you've been able to get to this step and the model has trained. And once we've trained our model, we can then actually use it, right? We can make predictions. There's a model.predict function. And here we're going to use model.evaluate, which will compute the loss and the accuracy on our held out testing set. And so for me, my final accuracy is 93.89. Hopefully you get something similar to that. The last part before we go to the breakouts is we are going to look at some of the input values that the model got wrong. So in model development, it's often really useful to look at where the errors are because it might give us some insight into what's happening within the model. So looking at these, some of these, I would say it's kind of understandable that the model got this wrong. This center bottom one, for example, you can understand why it might think this was a 9. It's very blurry and low resolution, so it's hard to tell the difference. This being an 8 also, it's very, very hard to tell given the small number of, pixel values we have here. But some of these other ones, it probably should have got correct. I think this is fairly clearly a 5. So it tells us that, 93%, but also some of the ones that it is getting wrong are ones that we might get wrong as humans as well. So we're close to the top end of performance here. Okay, so now we're going to move into the breakout groups. And there's a couple of exercises here. The first is to try different configurations of the optimizer, which is, again, the algorithm that's used to train, to figure out what the parameter value should be, what the weight value should be. So in here, you can copy the code that we worked on together, and you're going to change some of these values and see what happens. And then the second thing is looking in a little bit more detail at the raw predictions that are coming out of the model. So when we feed it the input, what does it actually look like? And how does the sort of real prediction, quote unquote, come out of that? And lastly, we're going to look at the initialization. So this was the great question from before about how do we make sure that the neurons learn different rules from one another. So they have to start with different random values. And in this section, we'll look briefly at what happens when we use different rules to set those initial values. So if we set them randomly, we'll see what happens if we just set them all to 0. Spoiler alert, the model won't work. Okay, Antonio, I see that there's a question.
Yes, when you were going through at the beginning the impact of the optimizer, it mentions the learning rate and the momentum parameter. What are those?
Okay, so we are a little bit doing the cart before the horse here because tomorrow we're going to talk about how the learning actually works. So we're testing it out, but we're really going to learn about it in more detail tomorrow. At the high level, the learning rate is how much we change the values in each step of the training process. So do we change them a little bit? Do we change them a lot? We have to figure it out as part of the process. And momentum is the idea that if we are consistently changing a certain parameter in one direction, then we want to keep doing that, or we want to accelerate that change because it probably needs to be, changed more. So if I keep increasing the value of one specific weight, then that tells me that it probably needs to be a lot higher. And so momentum helps us to do that. Calvin, question?
Yeah, is there a way to set, how do we replicate the results? Like in the past, we would set a random seed to a specific value. Is that something that can be done in here too?
Yes, absolutely. I think it's here in model.fit that we would set the random seed. I think that I would need to look up the specific syntax, but I believe that in the model.fit is where you would say random seed equals 32 or whatever you would.
Okay, thanks.
Okay, so yeah, as I said, I'm going to create breakout groups now. I'm going to try to create 6 breakout groups. This is time for you to work on the remainder of this lab on your own or together in the group. I often find it's useful for one person to share their screen and everyone work on it together. And then in those groups, we'll give you a little bit of time to just get set up, and then the three of us will come around the groups and talk to you and try to answer any further questions. And then tomorrow, when we go to the lab, I will run through the last part of this so that we make sure that everyone is on the same page. Okay, just give me 1 second to set out the breakout groups, and then we'll get going. Oh, I'm sorry. Actually, could one of the learning support staff create the breakout groups? Could you create 6 breakout groups?
I think we are in a big breakout group, right?
I'm sorry.
Yep, I think the rooms are open now.
Great.
Yeah.
Thank you. Jenny or Edward, could you please add me as host on the call so that I can jump between the
Yes.
Oh, sure.
I
Yes.
can give it to
No, no worries. Great. Thank you very much.
Also, shall we wait like for a couple of minutes before joining the rooms?
Yeah, I normally just wait. Normally I wait 5 or 10 minutes, but because there's only a little bit of time left, I would say, let's call it 8:18. We can start going between them.
Sure.
Okay, I think we can start going to the breakout rooms now.
Hi. We're in group 6 and we wanted to see if any of the learning support can join. I don't know if anyone's here.
Hello?
Hi, Edward. I think you're from the learning support, right?
Yeah.
We've been waiting in group 6 to see we have some issues with the kernel.
The kernel? Oh,
Yeah,
okay.
it's crashing.
For all of you or just one of you?
A few of us, yes.
Okay. Did you read what the error message said?
For me it was saying it's just crashing, and yeah, I don't know about the rest.
Did you copy and paste it or share screen?
But I was wondering if you can come to the group number 6.
You want me to go? Okay.
Yeah,
Sure.
and
I'll go right now.
how can I join the
See you guys. Bye.
I guess it's done.
Well, just us again. Maybe they didn't close the breakout room.
All right. Bye.
Okay. Good night, folks.
Bye for now.
Yeah.